Okay, so I guess we can get started. Thank you all for connecting. This is one of a series of talks that we've begun organizing over the past month or 6 weeks or so, focusing on AI machine learning and its interactions with physics in particular. So Kenji will talk today about the SCAILFIN project, which is an NSF funded project now since I think 2 years, right? A little more than 2 years ago this was funded, and I'll just pass it off to you.
All right, thank you. Thank you for having me today here. And as it has been said, this talk is going to be about the SCAILFIN project, and I'm going to talk about how we create cyber infrastructure in this project in order to run artificial intelligence and likelihood for inference algorithms on HPC resources. So, but let's start with the motivation for the project overall first. So as you know, major multi-user research facilities involve the comparison of the different data that you collect from experiments with simulated or synthetic data produced from computationally intensive simulations. And well, after you have that, you start the comparisons of this experimental data and the predictions of the simulation. And you have different examples of experiments, like for LHC experiments, you have Atlas, CMS, Alice, LHCb, neutrinos, there is IceCube, there is LIGO. And so these all have their own techniques for data analysis. And this data analysis is often conducted just uh, based on whatever the research is doing. So mostly on, in many cases, just through ad hoc scripts that might not be well maintained, and it might make reproducibility and reusability hard. So uh, it complicates things, but the thing is, many of these tasks are often well-defined workflows that you can automate if you put enough effort. And so RIhanna was created. This is another project. It was created in collaboration of DASPOS, Diana, and CERN in order to address the reproducibility and reusability issue. Now, in parallel, there has been a lot of interest in leveraging machine learning and artificial intelligence techniques to enhance analysis of data from these facilities. And there is this one in particular called likelihood-free inference techniques that you can apply when the predictions of the data are defined implicitly in the simulation. And so this can apply to any analysis of data from LC experiments, LIGO, or others. And this has been started, again, also mostly on ad hoc scripts because the training workflows are very complicated. And so this is where the SCAILFIN project comes in play here. We aim to deploy artificial intelligence and this likelihood-free inference techniques and software using scalable cyber infrastructure that is developed to be integrated into existing CI elements such as the RIhanna system. So this is a collaboration of 3 different universities. There is the University of Illinois, NYU, and Notre Dame. And this is my one slide on this simulation-based likelihood-free inference. So basically, we're trying to measure some parameter data, and we have observables X that you get at the end of a long set of interactions. So you measure something in your detector, and you want to measure something using this input. But this can be obfuscated by many different layers of different variables that this mirror or whatever. But you can, however, given these parameters and inputs, get some relationship that you can calculate between these variables and the ones you're trying to actually measure. So you can write that sort of approximation of a likelihood ratio function that allows you to distinguish between the individual parameters. Overall, this could be just an hour talk, and it's not even the focus of this talk. So I'm going to stop there. But overall, you have some training data derived from simulations. And if you want to get good results, you need to scale. So today's topic for the SCAILFIN is focused on how we extend this RIhanna platform in order to allow remote submission of workflows to HPC facilities. Now, SCAILFIN has, right now, we have two main components that we are leveraging on. One of them is, as I have already mentioned, RIhanna for the reproducibility framework part. And then the other component is called VC3. And this stands for Virtual Cluster for Community Computation. And this was another project that it's just in order to submit jobs to HPCs, and it handles different ways of authentication, and it can provide different software requirements for your workflows. So I'm going to talk about this briefly. For RIhanna, again, this can be divided into major components. You have the RIhanna client, which is what the user uses, and that's where you submit the workflows. You can define your workflows and then use this to submit them. And then there is the RIhanna cluster, and this is like the workhorse. It consists of many small pieces that handle the workflows. They split the jobs, they coordinate the results. And so you can sort of think about this as the job scheduler. And these jobs are scheduled via Kubernetes. Now for VC3, this is a platform, again, for just provisioning virtual cluster frameworks over heterogeneous resources for collaborative science. So this is like you're creating a layer on top of these different HPC resources, and you can use that single layer as a cluster just to submit your workflows. And the components for these virtual clusters, these different HPC resources can have different batch systems. So this is an schematic of the architecture for this VC3. So, but what you have is basically what the user sees is a website. And in the website, they need to enter some credentials for authentication. So they create some for accessing a dynamic head node that is created on the fly by VC3. And then they need to provide their credential to the different HPC resources they might have access to. And so what happens after the user enters all this is there is some info service component in VC3 that reads this and it propagates it in the infrastructure. It calls or it communicates with a master component that will provision the dynamic head node for the user to interact with. And then at the same time, it talks to a factory that submits a bunch of pilots into the HPC resources. And so the main feature here is that the user can select its own middleware for submission. So I mentioned again before that it doesn't matter this supports different batch systems in the HPCs, and the virtual cluster can have their own middleware. So this middleware could be Condor, or it could be others like Spark work queue, or in our case, we're integrating this with RIhanna plus HT Condor as the backend for the RIhanna platform. And some um, HPC, some batch systems that this supports are Torque, for example, Solorum, Condor, LSF, SGE, PBS. So there is quite a variety of batch systems that are supported. Now, let me talk about the infrastructure in RIhanna. This is the standard Kubernetes deployment for it, and this is based at CERN. So there is a CERN cloud based on OpenStack that uses the container orchestration engine in order to provision the Kubernetes. And the RIhanna cluster can be deployed via Kubernetes by the users that have access to this CERN node. And it basically has a different set of components that are running through pods in Kubernetes. And so the top part here in this diagram are basically the components for RIhanna. You have a server, a database, a message broker, and a workflow controller. And this job controller here this is the scheduler that is also using Kubernetes to schedule to the workers. So in the end, what you have is you start running your workflows in some machines at CERN that will all share some common storage, also using Kubernetes magic, and the workflows will be executed through containers via Docker. Now, of course, we can't use this, especially this part that goes from the job controller and schedule workers through Kubernetes on HPCs. And so there are other things also, like HPCs often don't support Docker because of security reasons, but they provide other alternatives like user space container technologies and like Singularity, for example, which is available in many HPC centers like the Pittsburgh supercomputing facility or Stampede, Comet. There is also Shifter at NERSC. There are other approaches like Charlie Cloud that in principle could be used anywhere as long as they support user namespaces. And that allows you to run unprivileged containers. If you have that, at least the Linux kernel 4.4 available there. And these alternatives usually have mechanisms to run or convert from Docker images, which is an advantage. So some of the changes that we have to make to RIhanna and to VC3 was like, for RIhanna, we needed to replace the support for Docker and with Singularity and Shifter. Then since RIhanna uses the Kubernetes API itself to schedule the work to workers, we replace also that, and we are using Condor as the backend. And also there is this job wrapper where we try to just detect whatever container technology is available in the HPC center, so you don't have to specifically. So,
Can I ask a quick question? If you see that there's, for instance, Docker containers or something, and you need to be using, say, Singularity, and you mentioned there are these kind of tools to help kind of convert the container. Is that something that could ever be kind of automated, like that conversion, or does that require some? I don't know enough about the converters.
Oh, in this approach, the conversion is handled automatically already. So you just provide like the Docker images, and it's going to handle that. Like in Singularity, you can directly provide the Docker image, and it does the conversion. And for shifter, I think we're converting it in the job wrapper before using it.
Okay, great, thank you.
Yeah, so the user doesn't have to worry about that. So, okay, so that's for RIhanna modifications. Then for VC3, we basically created a cluster template, and I'm gonna talk about templates later, so that we can have this RIhanna platform with integrated with Condor. And besides that, so we use this for the workers, but we still use the Kubernetes via Minikube in the dynamic head node that is provided by VC3 in order to run the base components for RIhanna, like the job controller, for example. And we have access through this as long as the some of the mechanisms supported in this approach are like SSH keys, also GSI SSH or SSH proxies that are used by Notre, for example. And so this is an schematic of the RIhanna cluster. Again, what you have here is what we change here is basically the job controller now is using the batch system submission for the HPC to the HPC center. And again, we use Singularity or Shifter rather than Docker. Now, besides that, I mentioned there is also a shared storage that was handled through Kubernetes Magic in the standard RIhanna deployment. So we had to replace that. And for that, we used something called sherp. I will talk about sherp later. And from the user's perspective, they interact with the RIhanna client. They just create the workflow. They need to upload their input files. And then once they start the workflow, this contacts the workflow engine for RIhanna, which will talk to the job controller. And then this will go to the worker. And the workflows are running inside some fixed paths that is supposed to be in the worker. And the problem is this is easy to do with Docker because it has root access. And if we create this/RIhanna in the head node, the VC3 head node, and if we had Docker and this shared storage through Kubernetes, then you don't need to do anything just to get access to that. But with the alternative container technologies, well, this is user-based, so you don't have that sort of permissions. So you need to use something different. So again, that's where sherp comes into play. And this sherp is a lightweight user-level file system, and it's used for collaboration across distributed systems such as clusters, clouds, and grids. And it allows an ordinary user to share storage space and data without requiring root privileges. And it has different authentication mechanisms supported. And also there is Parrot, which is a tool for attacking existing programs to remote IO systems through the file system interface, and this Parrot tool is integrated with sherp. So if you have Parrot, you can do things like the commands below, like Parrot run, and then VI, or copy files from somewhere to somewhere else using this sherp protocol easily. Now, the reason we chose sherp is because we, in VC3, we're using Condor as the middleware for creating this virtual cluster. And sherp is already integrated with Condor. So all you need to do is you just, and the user doesn't do this, we do this. We just add some class add, which is one IO proxy equal true in the jobs. And this makes Condor create a chip server that can be used between the VC3 head node and the workers. and it takes care of the authentication. So Condor handles all of that just by adding this line into the jobs in the job description file. And so that's for the chirp server. Then for the client, rather than just using the chirp client directly from Condor, we use this Parrot tool because we have there is a static version available that runs in any x86 architecture. And so we use that in order to interact with chirp and access and transfer data from the workers to the head node as necessary. Now, again, let's come back to this user's perspective, RIhanna client schematic. Now what we have is, this is the file system, and we share this through this chirp server. And now the worker runs using Singularity or Shifter, and we bind mount this area, which is basically in the user's home area, as /RIhanna user, so that there is no conflicts between the different approaches, the Kubernetes and this approach. So in principle, you could scale in the future some workflow that could use both systems. It could provision workers through Kubernetes and through these two HPC centers. Now, I'm going to show a few deployment examples. There is Blue Waters and NERSC. But before that, this is just a schematic of the templates that I mentioned before for VC3. So the user needs to, again, provide some user allocations into the HPC centers, and then they define a project. They choose a cluster template, and this cluster template, again, can be Condor, Spark, WorkU, or in this case, RIhanna plus Condor. And then they can define some environment that will provision specific packages that the workflow might depend on. So the part that we worked on is basically in creating this cluster template for RIhanna here in the middle of the schematic. And so what the user sees is they just go to a website and they need to register an allocation, one or more allocations. And here are some examples of the ones that are supported. And then they define, they need to provide the authentication mechanism. So here, for example, this is using this SSH proxy that is used for NERSC. They just need to copy and paste the private token into this, and they can get access to NERSC that way. There is some, well, I didn't put that here, but there is this private tokens usually get some expiration date. And so the users also can renew, they need to renew their proxy so that let's say, I have access to this for a week at least for each proxy. So every week you need to renew that, but you can do that easily through the website. And so this is what we did for Blue Waters. Again, we have this edge service, which is the VC3 head node. In there, we deploy the RIhanna components. So the server, the workflow controller, and more importantly, for this talk, the RIhanna job controller. Now this job controller talks to a Condor schd that is in this head node. And this will use Bosco. In Blue Waters case, it will use it with GSI SSH authentication, which is not available by default by Bosco, but we added that support. And it will talk to Torque, which is the batch system for Blue Waters. And then that contacts a mom node where you actually need to schedule the work to the actual compute nodes. So in the wrapper, we run there a pilot that will actually schedule these run the payloads into the compute nodes using shifter. And again, this there is the files are shared through sherp and parrot here. Now this slide is very similar. This is what we do for NERSC. In NERSC, this is handled through Slurm. There is no mom node here, so things are directly going from the query submit node into the compute node. And again, this approach is using shifter as the container technology. And yeah, Bosco here is just using SSH. Now, this is a test that we had running the Beyond Standard Model search example. And this just shows how the user works with the RIhanna client. So this is the work. This is after the workflow has already finished. So the user can look into the status, and then they can look into what the files are. They can download the files. The last part here is just showing the content history, just showing the jobs that were running, and this NID. These are the host names for Blue Water workers, actually. And just to give you an idea of the complexity of this workflow, here is the diagram of how this goes. So it is quite complex, and it's very nice that you can do this easily through RIhanna, because the workflow is already defined, and you just need to you can modify easily this through some YAML files, and just use the RIhanna framework to submit these workflows into the HPC centers. The slide here is just showing the results again after everything has finished. And yeah, now this example is not really a machine learning based example. So for that, we are using MapMiner, and this is a workflow that the other two universities are also using. So at Notre Dame, we focus on the remote submission part to HPC centers, and the other two are focusing more on the machine learning part. So what we have is a MapMiner version that backs from 2019, where we apply some changes, and this thoroughly worked. We tried this on different sites. We started at Notre Dame, then we ran it at Blue Waters, Nera, Stark, and PSC. There is a new version, which is more powerful, better defined, and it uses MLflow as part of for this, but we're currently dealing with some issues with MLflow when running this. So this is so getting the latest version for this to work is still work in progress. So in conclusions, we have successfully managed to run the MapMiner, even if an older version workflow on HPC sites. And the current version that we have for VC3 plus RIhanna is using the latest stable version of RIhanna, which is 0.6. Eventually, what we want is we want not to depend on the VC3 infrastructure. So we want to move some of the submission infrastructure from VC3 to RIhanna directly. And again, we're working on sorting out the issues with MLflow for the current version of the MapMiner workflow. Okay, so these are just some links for the SCAILFIN source code if you want to take a look, and the websites for VC3 and RIhanna. Thank you.
Okay, thank you, Kenji. Questions, thoughts from anyone? We're few enough. Probably you can just jump in and we'll resolve conflict, any collisions.
This is Kyle. I have one question in terms of the sort of same story with like, so we're working with people at NYU about trying to do something similar, but the HPC there is using Slurm, and so the thing that been asked about, which I'm not so super clear on, is when you have this kind of head node that's running like a small Kubernetes cluster, to kind of do all the orchestration, and then it's talking to the Slurm backend. There's the shared file system between those two different components, and my understanding is in the Condor setup, that communication is being dealt with using chirp. Is that right?
Right.
Yeah. So I don't know that much about chirp and stuff, but is that could play. I mean, do you know if you were doing this with like Slurm instead of Condor, how that would be handled?
Yes. So this is again, this works even with the Slurm. We use this for NERSC, for example, that uses the Slurm. So what we have is the HPC may be running Slurm, but in the top layer created by VC3, what we have is Condor as the middleware, and then Condor submits a pilot inside the HPC center using Slurm. But this pilot is running Condor std, and so this is the std that connects to the VC3 head node and talks and shares the files to the head node using Condor. So it doesn't really matter if the HPC center is using Slurm or Torque or any other batch system.
Okay, but they would need to have VC3 installed.
No, VC3 is like well, yeah, they don't need VC3 installed. What they need is a user account in the VC3 portal, and we can provide that.
Okay. Yeah, I don't know enough. I mean, I guess I'm just thinking about I don't know how connected they are to that, but I'm just thinking if you just have some random HPC site that has Slurm running, and you wanted to deploy this, so one is you're saying to try to connect via VC3 and then.
Right. Yeah, we can try this. Like the steps are basically you just contact me. I give you access to VC3, and then you have some website that where you can just put your credentials, and VC3 will create your RIhanna infrastructure on the fly, so that it can submit jobs to your HPC center.
Okay, but I mean, it's still going to require that. I mean, in that situation, the head node also needs to be. I mean, you still need to deploy all these things at the HPC center, right?
It's going to yes, but this is all handled automatically, so the user doesn't really deploy anything. It's just the user just needs to provide the credentials, select RIhanna plus HT Condor as the middleware in VC3, and then all the components are deployed on the fly automatically, and the user just interacts with the RIhanna client. So at that point, it's just the same as using any other RIhanna server available, like at CERN or like at NYU.
Okay, and but then the kind of the RIhanna server, where is that? I mean, like from the users, like the RIhanna client users point of view, is that like you aim it at VC3, or it ends up you aim it at like
this RIhanna server is running at in the VC3 head node, and the reason for that is that, well, it's not a good idea to run long-running processes on HPC front ends, because you don't know if the load is too high, they could just kill it.
Right.
And so that's why we have this sort of edge service. And that's why these main components are running independently.
Yeah. Okay, thank you. That helps.
Other comments, questions? So, one question, you talked about blue waters and so on, and there's, on the NSF side, potentially the other interesting place is TAC and Frontera, in part to sort of, have a demo to the connection to that, since that's the sort of, big deal facility, large facility for the NSF. Have you considered?
We have run attack too in the past, and we need to redo this because I don't remember on top of my head if the credential, the authentication mechanisms have changed. But yeah, we have been able to submit there in the past, so we should be able to still do it.
Okay, certainly advertising that.
There was also like PSC, so Pittsburgh.
Oh, right.
So that's somewhere that's another center we have submitted jobs to also.
Okay, so I guess then the other question that I had was this, may include people like Kyle, and not just. So what I think this was a 2-year project. Maybe it's no cost extension, still continue with it, but where does it go as the next step?
That's a good question. It's it is a 2 years project, and the 2 years have expired already, but it was extended for this year, so maybe for 10 more months or something like that. So right now we're focusing on finishing the integration of this, like scaling the miner workflows. That's mostly the next step, and also making this independent of the VC3 infrastructure. Because even though this is very useful for us, VC3, this is an infrastructure that is maintained at the University of Chicago, and it's not going to run forever. So we need to make these components work as part of the RIhanna infrastructure itself, rather than just using some external edge service.
Yeah, and then I think partially to answer Pete's question is, so there's been the first version of the miner workflows were done, and that was used for some initial prototyping, but then Sinclair, who's also online, did a lot of work to kind of refactor that and et cetera. And so I think what we've talked about is doing some kind of large scalability tests with the miner workflows, where it includes, event generation, machine learning tasks, the downstream things, and to try to do, some, pretty big compute jobs there. And then in coordination with like a few different sites where we would try to run that scalability, those kind of scalability tests.
Okay. Thanks. Other questions? Anyone? Comments? Okay, well, thank you, Kenji, and to everyone, have a nice afternoon, evening, wherever you are, and more soon. Bye, everybody.
Bye, thank you.
Bye.
Bye.
Bye. Cheers.
Bye.